Good morning, everyone. Today in this class, we are talking about a concept called terminal velocity. So first, let me try to explain and then define what is terminal velocity is, and then we will derive an expression for that. So imagine a kind of a water drop falling in air. So as it is under the influence of the gravity, it's obvious that its weight always acts in then a downward direction. It means it's having an acceleration, of course, due to the gravity acting in a downward direction. So, as the body starts coming down, as it is accelerating, its velocity will be keep on increasing. So, the velocity of the raindrop, say for example, while it is coming, falling on you, will be having an increasing velocity from the skies. But at the same time, there is an air. This air is a this all is air. So this air is having a kind of a is a nature air is a fluid. Then when a body is moving in a fluid, there is an upward force acting on the fluid, as you know, is called as upthrust. So this upthrust will be acting against acceleration due to gravity. So acting in upward direction, being the name itself. So its velocity will be slowed down. Not only that, there is another force called viscous force acts against the relative motion. As the motion is downward, the viscous force acts in upward direction. So if you notice carefully, when a raindrop or any body falling in air moving in a downward direction, it has forces acting on it, like downward forces weight, which is dominating. Upward force, upthrust, of course, is fixed, and viscous force. Let me find out what are their values. The weight, first of all. Weight, what is weight? You know, the weight of the body is mass of the drop into acceleration due to gravity. This mass could be written like volume of the drop, density of the drop into acceleration due to gravity. That's the weight. Then what is upthrust is? So if you notice, volume of the body is fixed, density of the body is fixed, acceleration due to gravity is fixed. So upthrust is fixed. I mean weight is fixed. What is upthrust? If you remember, upthrust has a formula as per the Archimedes principle. It's a volume of the fluid displaced, density of the fluid into acceleration due to gravity. But as you notice, as this body is completely immersed in this air fluid, the entire volume of the body is immersed in the volume of the fluid. Hence, volume of the fluid displaced is equal to the volume of the body itself, as the body is completely immersed in the fluid. For that body to be in that fluid, it will push the fluid away. How much of the fluid is being pushed away? As much is equal to the volume of the body. So, volume of the fluid is the volume of the body itself. Of course, density of the fluid and acceleration due to gravity. And if you notice carefully, this volume of the body versus volume of the fluid is also fixed. Density of the fluid is fixed. Acceleration due to gravity is also fixed. Hence, upthrust is also fixed. But look at the viscous force. Look at the viscous force. How much is that viscous force is? According to a law called Stokes' law, viscous force is, as we have derived in the previous video, 6 pi eta RV. 6 pi is a constant. Eta is the coefficient of viscosity of that fluid. That's the air that we are talking about. R is the radius of that bubble or a drop. V is the velocity. But as the body is coming down, its velocity will be keep on increasing. And so the viscous force will be keep on increasing. So if you notice little carefully, the downward force weight is fixed. The upward force upthrust is fixed, but viscous force is increasing. So what happens? The as we go, the upward force will be keep on increasing this viscous force. So somewhere this upward force balances the downward force. Hence the body acquires a constant velocity. That constant velocity is called as terminal velocity. So I can define terminal velocity now. It is simply constant velocity acquired by a body when it is moving in a fluid under no resultant force acting on it. Or in a fluid, when a body is moving, somewhere resultant force acting on that becomes zero because of increasing viscous force. Then the body acquires a constant velocity. That constant velocity is called as terminal velocity. So what we can say at terminal velocity, the upward force, the downward force weight is balanced by upward force of thrust and the viscous force. That's the place where the resultant force acting on it is zero. Body acquires a constant velocity, and that constant velocity is called as terminal velocity. Let me write these values that we have discussed just now here. Let me substitute them. See what happens. Weight is this much. Volume of the body, density of the body into gravity equal to upthrust this much. Volume of the fluid, but that's equal to the volume of the body because body is completely immersed in the fluid. Density of the fluid and gravity plus viscous force. 6 pi eta r v. This v I call it like v terminal because at this junction it has already acquired a constant velocity. So I'm calling that velocity as terminal velocity. So if you rearrange volume of the body, density of the body minus density of the fluid, if you get this term to this side, g is common, is 6 pi eta r vt. That is terminal velocity. What is the volume of the body? Being it's in a spherical shape, 4 by 3 pi r cube, where r is the radius of the drop. Density of the body minus density of the fluid, and gravity is 6 pi eta r terminal velocity. We can cancel things a little. Two twos and two threes. Pi and pi also can be cancelled. One r can be cancelled in this r cube, so r square will remain. So what is remaining then? 2 by 3 is remaining out of r cube. R square is remaining. Density of the body minus density of the fluid into gravity is 1 3 is remaining here. Pi got cancelled, it is remaining. V terminal is remaining. So what's the equation for V terminal velocity? Simply get all these terms to this side. That's 2. 3, this 3 also come to the denominator. 3 and 3 is 9. R square, density of the body, density of the fluid into G by coefficient of viscosity. That's the expression for the terminal velocity. That's what we are intended to derive here in this video. So, if you observe carefully, this terminal velocity depends on, say, 2 by 9 is a constant, coefficient of viscosity for a given fluid is constant, acceleration due to gravity is constant, density of that fluid is constant, density of the body moving in the fluid is constant. So, only variable is radius. So, terminal velocity is directly proportional to square of radius of that drop. Bigger the drop, bigger the terminal velocity. That's it. That's what the important point is. You know, you will see this playing an important role. You can see it, you can experience it in your daily life. Say, for example, I'm just telling you a simple example just to conclude. Imagine there's a cloud on your surface. It's at least, say, imagine like some 5 kilometers above your head in the sky, at least, right? And from that, a raindrop is falling on you. So as for kinematics, it's going to have a velocity v equal to root 2 gh. How much is that? 2. G is approximately 10. 5 kilometers, that is 5,000 meters. So there is 4 zeros, 2 zeros will come out of the root. 2 into 5, 10, even approximately 3 threes are 9, 3 will come out of that. That's approximately root 300 meter per second. So a raindrop falling from a cloud going to strike your head here with a speed of 300 kilometers, which is even bigger than a bullet. That's gone. You are gone if that's the case. That's not happening in real life. Why that's not happening in real life? Because when this raindrop is falling on our head, there is a great viscous force. who is acting upward, who is helping us to survive, right? So viscous force of the nature of the air is actually a kind of a protection that is given to us from the nature itself. That's how you need to understand viscosity and terminal velocity. Thank you for watching.